Good morning. I'm Bill Engelke. I'm with the University of Alabama Center for Advanced Public Safety. This center is part of the was part of the computer science department. Now it's on a par with the computer science department because we're actually bigger than the computer science department now. We have about 125 people, software developers, business analysts, system engineers, and one guy involved in actual research. That's me. I have done some work with commercial vehicle law enforcement, designing virtual way stations, but now I've got a little bit of freedom on some IR&D work we're doing to do a little bit of ionospheric work. So what I'm going to talk about, let's see, how do we go next? This button. Okay. A little bit of overview. What I'm going to talk about, Sporadic-E and Sporadic-E propagation are kind of two different things. I'll tell you what I mean in a minute. I've done some classical statistical analysis using data collected from what we call the HARC database. If you're familiar with this, we're collecting data from RBN, PSK, the DX cluster, and WhisperNet, all into a database. And I can use that to basically observe propagation because I can determine the location of most of those spots. Those are spots. Somebody heard a signal, and I generally can tell where the signal came from and where it ended up. So, and by doing certain filtering on the data, you can determine where that signal, well, assuming short path, the path of that signal. So, my classical statistical analysis to many different kinds of physical phenomena really hasn't yielded any results, and I'll tell you why in a moment. So it occurred to me maybe I could try some things from deep learning and see this approach is just now being prepared. I don't have results yet. I hope to, by the fall or early next year, have some actual report of some actual results. So a lot of work in studying GPS occultation has shown that a certain amount of Sporadic-E is happening a lot of the time, if not most of the time. And very often it doesn't result in 6-meter propagation. Now, how do we know that there's a Sporadic-E is occurring? GPS occultation is a technique by which you can observe a GPS satellite using another low Earth orbit satellite. And GPS outputs 2 different frequencies, and by measuring the phase difference between them, you can do like the total electron count between them and observe the difference in refraction of the different frequency signals, and you can get a pretty good estimate of what the Sporadic-E. So that allows you to measure that. Now, what causes Sporadic-E? There's a couple of different major factors that we know of, at least what the theory is. Metallic ions appear in the atmosphere because of metallic micrometeorites and meteoroids burning up in the ionosphere and leaving metallic ions. These then are supposedly drawn into sheets that by ionospheric wind shear and Lorentz force, which tends to guide the particles based on the Earth's magnetic field. There's another factor, that is the Equatorial Electrojet. Electrons pushed by the sun's ionization move in a current from east to west above the equator, and as they fall down as they get further away. Now, there may be additional factors, and that's what we're trying to get at. What are some of the additional factors? And because why do we sometimes have 6-meter propagation and why sometimes we don't? Now, there's been a theory advanced by Joe Zekovich, K1YOW. There was a QST article in December of 2017, which you might have seen, in which he theorized the possibility that maybe upper-level lows, now this is down low, but the idea is that perhaps when you have a strong enough storm, there's enough energy to drive ions all the way up into the E level. And then maybe the jet stream has to be a certain way. Ionospheric winds may happen fall within certain ranges. I've gotten some data from the TIDI satellite, and I've found out that if ionospheric wind shear gets above a certain level, then your 6-meter propagation starts to drop off. So maybe these winds need to fall within a certain range. So what Joe Zekovich calls this is maybe there needs to be some kind of a Goldilocks zone in a lot of these parameters. And that doesn't model very well with straight linear regression or multiple regression. Why have I not been able to correlate a lot of these things? Just those reasons. Maybe some of these are non-linear. Maybe I'm not looking at the right factors. We've lots and lots of data. You got a lot more data now than you used to have. Oops, my linear regression doesn't work because that's totally linear. Maybe some of these things are non-linear, and there may be that propagation is enhanced by specific patterns of factor. So too much or too little of one or more parameters may disrupt the ability to get 6-meter propagation. So just a little bit more detail on what Joe has theorized. He mentioned a time of great propagation between the United States and Europe that occurred in mid-June 2016, and identified a couple of upper-level lows that occurred. One was off above Newfoundland, and one was down near Iceland, forming a sort of a path of ionospheric conditions, perhaps created by upper-level lows running between North America and Europe. Maybe. Now, I'm not convinced that this is really what's going on here, but I'm going to figure this out. Now, it requires that in order to analyze upper-level lows, I have to take a look at weather maps. It was suggested to me that I work with the raw data on the raw, I guess you would call barometric data, isobar data, and this kind of thing. What I found was the raw data is almost well-nigh impossible to work with. Finding what you need, it's scattered all over the place, all kinds of different data formats. Our favorite data format, HDF5, is available for some stuff, but in many cases, a lot of the weather data has been stored for decades, long before HDF5 was conceived of, and then trying to interpret that is very, very tough. What can we do? So how can we analyze data, all these different data types, including the weather data? Well, let's take a look. It occurred to me I could use something called deep learning. Now, this is a branch of artificial intelligence. Now, when you think about artificial intelligence, what automatically comes to mind? Automatically killer robots and this kind of thing. But, having worked with AI and robotics a little bit, I'm not quite as worried about these because it's so easy to break them. One little thing wrong and the whole thing doesn't work. So anyway, my deep learning uses a technique called a convolutional neural network. It learns patterns by being trained on thousands of examples. You can use it for linear regression analysis. It'll find linear patterns very nicely, but it can also find nonlinear relationships. So my objective here is to be able to forecast a result based on a pattern of inputs and then know the confidence of the prediction and thus gain insight into the science. You can do some things, I'll put it this way. An AI system usually is not very good at telling you why it knows what it knows. It just knows the pattern. But by varying inputs, you can determine what it has found by way of patterns. It will, in terms of classical linear regression, all of your different factors have coefficients. Coefficients that don't impact the result, the coefficients tend to slide towards zero. And an AI system will do that for you very nicely. So what data do I have to use? As I mentioned, I've got 6-meter spots from 4 different sources. In order to filter these down so that I actually have a set I can actually work with, I'm going to specify that one or the other of the stations in the spot must be in North America. That allows me to exclude transequatorial propagation. What constitutes 6-meter E-skip, sporadic-E propagation? This is one of these things where you can make a lot of selections on this, but I have to start somewhere. I'm going to use spot distances running from 1,500 kilometers to 6,200 kilometers. 6,200 kilometers is given as the upper limit for Sporadic-E. The lower limit on that, you'll hear different things ranging all the way from 500 up. I'm going to start with 1,500 because there's a lot of meteor scatter data that falls in the smaller distances, and I would like to exclude that because that's not Sporadic-E. So 6,200 kilometers should also exclude most moon bounce, I think, I hope, I guess. I don't know. You can also look at frequencies because they tend to do these kinds of frequencies in certain bands, sub-bands. So we've got a lot of data, NASA data, mostly solar. We've got irradiance data. We've got UV data. A lot of that, it's, you know, since 2016, the UV data is pretty weak, almost non-existent because they've been struggling with some of the sensors on the new satellites and really not ready to certify, yeah, we've got the data. But I'll tell you one thing that turns out to be very useful is meteor impact data. I've found more of a correlation between meteor impacts and 6-meter propagation than anything else, which, going back to the theory of metallic ions in the ionosphere being a source of a source of Sporadic-E, that seems to work. Oh, we have a lot of NOAA data, particularly weather maps, and we have ionospheric wind shear data. So that's where my data set is to begin with. So let's talk about how you actually do this. Now, I'm going to go through this very rapidly because it's a data science topic which is not that interesting to most of this audience. You can see me about it later, but just in short, you have to get your data from various sources. You have to be careful about what data you select. You have to get it from all kinds of different formats, and then you try to normalize it. You clean it up. Ideally, the software I'm using, which is TensorFlow, it's a freeware that comes from Google. You would like to have all of your data in the range between 0 and 1 floating point to as many decimal points as you can stand. You have to try and get your data to a common geographical area. And then summarize by epoch. And so, since I've got weather maps, in most cases 2 of them per day, at 0 and 12 UTC, I'll get a summary of the spots. Well, actually, I'm getting it every couple of hours, but I'll summarize it so it's twice per day. So we've got 2 trainings we have to do. Once for the upper level load detection, and the next for the data analysis itself. So step 1, I'm going to do image processing to find the upper level lows in weather maps. So first, I have to decide what constitutes an upper level low. Well, it's easy to see them on the weather map, but so many times you see these on a weather map where they don't correspond to 6-meter propagation. So I think I can probably start by selecting some upper level lows that occur on known high propagation days, and then see if those upper level lows are particular or special in some way. So you have to give your training system something like 500 examples of an upper level low image. Now, I don't know if I'm going to come up with 500, but I can come up with some number. Then use a trained model to count upper level lows in several years' worth of weather maps. So here's an example. You see an upper level low here. Oh boy. Here, push the button and hits them both. And the weather map prior to this. Okay, here's a weather map before we've run the object recognizer. So what we're recognizing for is upper level low, and it puts a block around it. So you can count, it will give you a quantity of them, and you can even get the locations of them. So that'll give me one of my columns in my major data analysis. Now then, I'll set up columns for all the different things that I want to try and take into account. Ionospheric wind shear, peak wind shear for that 12-hour period. The number of spots, things like the extreme ultraviolet intensity during that 12-hour period. the geomagnetic index, and other things like that. So in order to train a convolutional neural network, we split the data into three parts. First of all, training data, that's 70% of it. Then test data, that's 20% of it. The way the system works is it creates a set of layers, and it sets the convolution of the layers to match the training data, and then tests it against the test data. And it continuously changes the mapping between the layers so that the test data comes closer to the training data. And then the two of them give you a confidence. Now, when I'm done, I want to take 10% of data that I have put aside and test to see now if the trained network, how accurate is it in identifying the remaining 10% of the data. It may show nothing, but that's a result too, I guess. Optimizing training can be really a royal pain because TensorFlow has so many different, in picking the number of layers, the number of neurons, the function between the different layers. If you're trying to figure out all those details is going to take some time and maybe even trial and error, I guess. And each time you do a training, if you're going to run it even with a GPU, it can take anywhere from hours to days, but it can take weeks if you're starting off from scratch. So we're just going to see. Nowadays, if you're going to set up one of these convolutional neural networks, you try and find a neural network that's partially trained and then add to it. So, when we'll do a sensitivity analysis. So anyway, I'm pretty much out of time here, but as I said, the objectives here are to understand the relationship between the parameters and 6-meter sporadic-E propagation. And I hope someday to be able to forecast, well, today's going to be a good day. If I can forecast that well, then I'll know I've figured out what the parameters are. I hope to have results within 6 months to a year. So that's my talk. Thank you. Got time for maybe one question? Phil? RMOB. Look, this is a network not unlike our proposed personal space weather thing, except people have slaved radios to their computers, and there's an algorithm that you measure some data regarding a local FM station or a radio station, and then you can identify noise in it. That was a meteor ping, and then this data is collected. That's what they're doing to detect meteorite impacts. rmob.org. One more?